completed or attempted all the problems in section 2.1 of FIS. It was a lot of work. Just as the last update, it's a little bit longer than what I would consider a week, maybe a week and half a day, you know, something like that. So, and I did not watch any more videos. I think I'm going to try to just keep on plodding along, making progress, and then this will be leisure, because it ties into Huffman and Kunz, or Kunze, which is a book that I want to look at later. But yeah, so then this was, I read the section, of course. Of course, these videos are all, I've gotten a little bit ahead because of the holidays that I've gotten, full days that I've had to work with. And so, but really, if you're timing yourself and you're doing something like this with this book, these updates, the last two, were a little longer than what a week would be, but they're coming out a week apart because I do have a little bit of, you know, I'm a little bit ahead of my schedule. So this will be going out December 11, and I did a total of 42 problems, 29 proofs. I'm at 183 problems and 113 proofs. A few of the problems, I've counted 2 proofs for the single problem, so these don't map one to one, but I haven't done that more than like 2 or 3 times. Okay, so then this is section 2.1, which gets into the business of linear transformations. And our friend Halmas is here for a reason, because I was able to use Halmas, and I will continue to do so. But the same as I do not want to start on Robman or any other baby abstract analysis, abstract algebra book. I'm not going to double book at all. I learned that the last time with all those analysis books. It nearly killed me. So linear transformations, proving that something is a linear transformation. Now the way this book does it is different to Anton. It doubles it up into one thing, ct of x plus t of y, instead of doing t of x plus t of y and then ct of x separately, which is really the definition for a linear transformation. So it's kind of like a twofer way of doing it, which is great, works fine. Rotation, simple transformations, and then of course the null set and the range. Figuring out which sets have something other than the 0 vector for the null range, something other than the entire range for the range. And so there are a couple of really good examples. Then the proof of a dimension theorem, which is really dimension of the vector space. The from vector space is equal to the nullity of t, or plus the rank of t, or the dimension of the null space and the dimension of the range. Then of course, if the null range is 0, the 0 vector, then t is 1 to 1. And of course, for onto, you just have to make sure that everything in the range maps back to the original domain. There's something plugging to from your range back. Some pretty good examples. And a theorem of uniqueness. So there's one linear transformation, T, for the basis of V having the same number of vectors as the basis of W, with a function that maps from each individual V uniquely to each individual W. So very nice proof. Then the problems took a long time, really tedious, but I loved it. I think it was, yeah, I just had a lot of fun. I'll just go through them. And then of course, the very last problem, and I'll mention it also when I go through with the solution, tells me that I did the last problem of section 1.6, for which I did all that reading and all that Socratica. I did this correctly. I was able, once I did this one, and also I read in Halmas for what did I read? Well, I read a lot from Halmas this time. I almost considered taking notes, but for quotient space. And I'm not going to look for it, but this book is just getting better and better as I finally have done enough linear algebra to be able to read good chunks of it, if not the whole book. I think I'm going to read this whole book at some point. I am not sure, because I know that I always am very eager to read 20 books on the subject when I'm right in the middle of it. But eventually I just get worn out and or want to move on to something else for this first round of math. So for the work itself, again, just the reading that I showed for section 2.1, just my notes. Of course, I always write down this diagram just to keep it in mind, linearly independent basis, and then generating set or spans. Then I started on the problems, screwed up 2 of the true and false, got confused a little with rank and nullity for some of the problems. I'll have to go back to these when there's more for the next book. I think I'm going to do one more linear algebra book, I think so. Yeah, I didn't do something right here, and I got something wrong here, so I repeated the problem, kind of mapped what all the different values were for the problems for which there were answers in the back, 2, 4, and 5. Sort of tried to correct myself as to why I screwed up, and then just continued on. And that was the only really major problem that I had. Everything else was straightforward, and I did this correctly as per the answer in the book. And of course, proving that something is linear gets a little tedious, but it's a good exercise, and that's what you're being asked to do. This one, I beat it to death. I just threw a hammer at it and wrote a very long proof. And when I looked at the answer was a lot simpler. I really only needed to do very little for this proof. And I think this is correct, but I went in a different route. So I gave myself a half a point because I don't really know if this different route is completely equivalent to the proof that was given as the answer. I think it is, but I don't know enough to say so. Yeah, more proving things are linear. And then the whole business of 2 sets, whether they were, and let me show in the book. So there were several subsections of problems for section 2.1. So one group had the definition of a projection of a set of a vector space on one of the subspaces or along that, which is really just getting rid of an axis. Really, it's just getting rid of an axis, and then the restriction. So the T invariance. Then I read a lot about invariance in Helmholtz, and then the some problems on direct sums. Yeah. So each one of these sections had its own flavor. They all seem to me doable. Just drew a lot of diagrams for how the sets were. This is done in much more detail in Anton. Yeah, more proofs for where something lands and what the null set is and what the range is and what are the relationships between all those sets. T invariance. And of course, I'm not sure if I did it correctly, but in the case of infinite sets, when you go from finite sets to infinite sets, I tried to use the argument in some cases where infinity plus 1 is equal to infinity, and so things are not exactly the same as they would be in the finite set. Or infinity plus infinity equals infinity means that something's not right in the infinite case. And this is why some of the relationships don't work in the infinite case and they work in the finite case. So I think. So this is a whole work, of course, that will have to be verified at some date in the future. Yeah, here it is. So you're asked to show why, yeah, right here, why it's not true that you can do a direct sum for the infinite dimensional case. And that's why I put a little square in here. This needs to be checked. Not sure that I got it right. Then some of the other latter problems were pretty straightforward. There was a very long hint on problem 40. I don't consider this to be a correct proof, in the sense that I basically regurgitated the hint and kind of saw that it is true that the trick that they give you in the hint does allow you to find in R to R that it can be additive, but it is not linear, because the C times T of X is not equal to T of CX. There's some trick that they have in the hint, but I didn't really do enough to consider myself to have done anything special. And I think I did get this correct, having to do with quotient spaces.